Good evening, everyone, and a very warm welcome to those of you joining me here in person in the Morley Room at the University of Northampton and virtually for the Professorial Inaugural Lecture by Professor Michael Opoku Agiman. I'm Professor Enrico Day, the Vice-Chancellor of the University. As Vice-Chancellor, it gives me great pleasure to celebrate the achievements of all of our staff who have excelled in their chosen field, and particularly those who have gone on to achieve professorial status, whether this is through exceptional efforts in research, learning and teaching, or in enterprise. Now, joining Michael, there are some very special guests with us this evening. I would like to officially welcome Michael's wife and their children. Family members are often the unsung heroes of any professorship, and I offer you a very warm welcome to the university. I would now like to introduce Michael and his lecture. Michael is a Professor of Computer Engineering in the Technology subject area in the Faculty of Arts, Science and Technology. He is the Programme Leader of Computer Systems Engineering, a Chartered Engineer of the Institution of Engineering and Technology, Chartered Manager of Chartered Management Institute, and a Fellow of the Higher Education Academy. Michael represents the research community of the university on the University Senate, and he is the Science and Technology Postgraduate Research Lead for the Faculty of Arts, Science and Technology, and a Chair of the university's PGR Supervisory Forum. You can tell we keep him very busy. In his subject discipline, Michael has a PhD in Embedded and Distributed Systems, Electrical, Electronics, Computer Engineering from Glasgow Caledonian University, and the MSc in Embedded and Distributed Systems from London South Bank University. Michael received his BSc in Electrical and Electronics Engineering from Kwame Nkrumah University of Science and Technology in Ghana. In addition, because that's not quite enough, he holds 4 teaching qualifications, including a postgraduate certificate in research degree supervision from the University of Northampton and 2 management qualifications, including the Executive MBA, also very sensibly from the University of Northampton. Michael has over 10 years of experience in embedded systems design. Previously, he was with Intel Embedded System Research Group of the Chinese University of Hong Kong as a research fellow, where he worked on reliable wireless network on chip and other innovative multi-core system on chip solutions. He is the author of over 80 peer-reviewed publications, 5 books, 2 book chapters, over 16 journals, and 32 conference papers. That deserves a round of applause. Yeah. Michael has won 2 best papers and 1 best paper in poster session at reputable international conferences. Michael's research interest spans across 3 main strands and disciplines: electronics and computer engineering, business and management, neuromarketing, advertising and market research, and pedagogy, education research. His range of academic interests include the Internet of Things, smart farming with a focus on vertical farming, smart grid and smart metering, problem and project-based learning, active distance learning, technology-enhanced learning, teaching multidisciplinary groups of students, decolonizing learning, teaching and assessment, experiences of ethnic minorities in education, equality, diversity and inclusion in higher education, the GEM Award and education gap, virtual reality and digital advertisement and marketing research. I think you should be doing my job and maybe I should be doing your job. He has been a guest editor of the EAI endorsed transactions on industrial networks and intelligent systems. He is a technical committee member of over 10 conferences and a reviewer of several conferences and journals. He was the first ever winner of the Diamond Early Career Research Award at the University of Northampton in 2019. He is also the winner of the University of Northampton's 2018 International Changemaker of the Year Award. This evening, Michael's lecture is entitled Asking for More. Please welcome Michael to give his talk.
Thank you, VC, for such an honorable introduction. And thank you, everyone, for making it both in person and virtually as well. So my name is Michael Opukwajman, and yes, I'll be asking for more. So Moore is an interesting figure, and we will talk about him in a couple of minutes. But I think for me, the title serves me in so many aspects, especially including my journey to where I am right now. And speaking of journey, I get to skip this because we've talked about quite a lot there, but at least I have to acknowledge the two research centers that I'm leading, which is CAST and CARE University. And I know things may change very soon, but I'm co-leading CARE with Paul, who is here as well. And I know Prof. Stefan is online, and he's assisting in the leadership of CAST as well. And I'll acknowledge the GEM staff network as well, who I'm co-leading the research team with Nathan and Patrice. So it's really hard to find a childhood picture which is not embarrassing. And these are the two things that I can settle with, right? So my journey actually began, I would say, well before I was born. But my dad, who likes to fix things for a living. So I've got my brother and sister here, and I'm sure they can testify to that as well. So as a kid, when I go to his workshop, he would give me typewriter machines, mostly to take apart. So I was really good at taking things apart, and he was good at putting them back together. I don't think I got it quite right in terms of putting things back together. And as you can see, he was training others as well, so one way or the other, teaching. And that opened many doors for me, but I would say one thing that actually impacted me so much was the fact that I know with technology changes really quickly, so you have to adapt. And I saw an old man in his 70s learning how to use computers for the first time. And luckily, with his background, he could fix things that he probably couldn't understand. And he got to a time where I was doing mostly the software and the hardware part. But in terms of how my childhood has been, it means that at home, there were lots of these things to play around with, lots of computers lying around everywhere. But I owned my first one when I got to university. But it means I got to also take a lot of computers apart. And interestingly, I get to put a Sega Mega Drive next to a typewriter machine because I would save my pocket money to buy games, and he didn't like me playing games. But I always had some hiding somewhere. So if he sees this one when he's out of the house, I'm home alone, I get to play more. But then I'll say, thank God for siblings, and I'll get to embrace my siblings here. When I was young, I was really intrigued about how I can create these games. And I asked them, I said, what do I have to study? And they're like, yeah, it takes a team to, no, what do I have to study to get? Yeah, it takes a team to build all the, yes, okay, computer science, electrical, electronics, engineering. You sort of need that background knowledge in life, great. So at home, I get to play with a lot of Windows 95, Windows 98. Windows 98 really hard to format for anyone who is familiar with. But that's where my computing journey started from. And now I look after both computer engineering and electronics engineering. Mostly, I'm a computer systems person, focusing on embedded systems. So it means that I get to take various aspects of the computer to focus on and play with. But before we zoom into that, just really, really quick history, and we'll come back to why we say more. Just blame it on my accent, I call it more, right? So we started off from various generations where we had mechanical computers all the way to computers that were the size of rooms, and these computers, their performance compared to mobile phones these days, nothing compared to it, but that's because they had vacuum tubes. Then came another generation where we could integrate more things on a chip just by using transistors. So just think of transistors as the building blocks or the basic building blocks of digital electronics or computers, right? Then came a generation where we have more of these transistors that we can put on a chip or integrated circuit era. Then that era made it possible that we can have smaller computers and more realize something, which has been the driving force of mostly the computer science industry, or those of us who focus on building the next generation of computer architecture, right? So he realized that the transistor density, which is the building blocks of these computers, we get to put more building blocks per unit area. What that means is that we get to have more functions with these little devices, which is why basically I can run Word or play a lot of games on this, because we have more powerful processors sitting on this. And this trend that he realized is basically every 18 months, right? So the idea is every 18 months, we get to increase the transistor density on these integrated circuits, right? And also that has also influenced something. If you realize, most people will say, I'm going to wait for maybe 2 years' time to buy the iPhone that is out now because it's going to be cheaper. So that has also influenced cost a little bit. There is another law also by someone who is also from Intel, and by the way, Moore is one of the founders of Intel. Intel is one of the biggest processor manufacturing companies, or just think of it as IC manufacturing companies around. So there's another law which is by Rock, and she basically says that, you know, as we come up with these new technologies, or we put more transistors or put more building blocks per unit area, the cost to manufacture them will also increase. So it means they are fighting against each other. For one to be true, the other one has to fail. But everyone, or every scientist in my area want to make Moore's law possible. The good thing is that in the past, this was fairly easy. So we could see that that's the building block, the transistor size. We can put more transistors, meaning we can put more functions per unit area. But it gets to a point where it starts to fail, it starts to scale up, right? And this is basically around 2010, 2005 range. But that's because there are a lot of other factors affecting it, and some of these factors is actually also the clock speed, because we can't make the clock speed any faster. So if you think about it this way, let's say if you take a computer like a human being, you've got a brain, which is the processor, doing all the data crunching for you. You've got a heart, the clock, which is constantly beating at a specific speed, right? And most, like the way that when your heart beats, it pumps blood to other parts of your body, the same way that the other parts of the computer that are synchronized to the clock. So the clock needs to be able to keep up. If you just keep making the computer faster, processor faster, 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 other parts, if other parts don't keep up, there's no way that it's going to keep getting faster, right? So we have a certain trend where those who have been buying computers for a long time will be familiar with Pentium 1 processors. We go to Pentium 2, Pentium 3, Celeron M. Then it gets to a point where we put more than one processor on a chip, because we just can't keep making the individual ones fast. And we have to come up with new solutions, and that comes with multi-core error or many-core error, because now we have thousands of cores that we can put on a chip. And that's also the area that I sit at. So that takes me to my PhD. This was started back in 2010, so going way back, and trying to make Moore's law possible. And I'll take this room for example, right? So we've got to the point where we can put more processors on a chip, right? The problem is that if we put more processors on a chip with the traditional system, which is the bus-based system, think of it as only one person can talk at a time. the processors are working on a task for us, right? So they are doing the data crunching. We are sharing it across. We need to find a way that we synchronize the way that they work, right? So if only one person can talk at a time, it's really difficult for us to continue the speed or more slow that we are aiming to get. It's difficult for us to keep making processors faster. So we adapt the idea of computer networking at the nanotechnology level or on the chip, which means I can say what I want to say to John, he'll go through a relay, something else will handle that for me, okay? But that opens new problems. The problem is that we want to keep making devices smaller, we want to have more functions on these devices, and we are going to introduce more onto the chip to make it possible. And these things take space, right? The router, all it's doing is sending information to the right person I want to send it to. So it becomes a problem of area optimization. And at the same time, if we are in this room, everyone is super active, this place is going to get really hot. And these devices rely on battery. So we also have to find a way of optimizing the power or energy usage, because everybody wants to take the iPhone to come somewhere and not continuously charge it, right? So it's a power problem as well. And already we've established that it's also a performance issue as well, right? So it takes me just from looking at how I can make computers better to how I can adapt a little bit of communication or computer networking on the chip as well. Then here is the thing. If John wants to speak to someone sitting at the corner there, it will take several hops or several hops for several relays before the information gets there. Wouldn't it be easier if we can pick this particular row and put it on or this particular column, put it on the others and stack them also on top, so you can talk to someone next to him and someone on top of him as well. So that takes us to the idea of 3D chips. So basically, these microchips holding many processors or many brains of the computer, we're stacking them on top of each other. So that takes us to the 3D technology. So eventually, it takes us to this field. That's the 3D IC with a bit of networking there and looking at many processing elements, all with the idea of making computing more powerful or computing power more powerful, minimizing the area, making them last longer in terms of on battery or power usage. And that's an issue I had to solve for my PhD side. So I didn't touch the wireless networking part quite yet, but we'll talk about that a bit later. And I worked with two Ali's for my PhD. They were my supervisors, and came up with various solutions, right? So in here, it's just basically saying, processor doing the data crunching for us, right? So if everything I've said doesn't make sense, think about it this way. The processor is your chef, because it's doing all the cooking for you. In my world, it's just zeros and ones, but it gets the menu, does the cooking, and then this part can get really hot. The more it has to do, the hotter it gets, right? So if we are putting several processors together, there are so many issues, so many masters in the room. We have to decide who is cooking what or who is doing what and how we coordinate that among ourselves, right? So on that, came up with, in the 3D network on chip world, came up with some solutions, but I like to view it as a Donkey Kong problem, right? Because the idea is I have to start somewhere here and I have to get to a certain end in terms of how I send the information. But it became a Donkey Kong problem because if we look at the original or the traditional system where everything is homogeneous. So homogeneous, you think of it this way. You have a story building and each room has a lift to the next level. And this one I'm looking at homogeneous in terms of the network architecture itself. These lifts are very expensive. So if you look at the chip, when we stack them on top of each other, the holes that we make to the next level, they are very expensive. And sometimes the yield is also low. So some initial experiments actually show that most of the time, these lifts are not busy. So it means we can get rid of some of the lifts and solve the problems that it creates by still keeping the performance and then also making sure that we shrink the size of these new processors to make it work. If the image on this side, all it's showing is that even if every room have more lifts, right, the processor will actually need more power, means our devices get hotter. So I spent most of my PhD time solving this Donkey Kong problem, but on the chip level. Managed to come up with various solutions that will still reduce the number of lifts or the number of holes, and then keep the performance and also save some power and also reduce the energy. And that's where I spend most of my work. And the end product was actually a software which I designed, and it allows you to put in your restrictions or your constraints in terms of number of processors you need, number of holes you need, and then it makes it easier and it will tell you the performance in terms of how much energy you save and other things, right? And I think hopefully this is the most technical stuff I'll be talking about today. So if you've understood up to this point, we are good. Right? Okay, so that led me to Hong Kong. And in Hong Kong, I work with Terence. Terence is with Southampton now, and he was my line manager in Hong Kong. And when I joined the team, Terence mentioned that he had a project running, which was using a particular wireless technology, but added to this area of many core systems and trying to solve the problem with it. So I had to find a way that shows I'm the senior researcher among the team members there. But I would say one thing I really, really, really remember from Hong Kong and the team is that amazing team are really, really good. So that's my take from Hong Kong. So during my time there, we worked with a bigger team, both in Hong Kong and then UK and other parts as well. And what I noticed with so let's start with wireless communication, which is simply you can send information wirelessly. So we have an added advantage, right? And we have the added advantage of the wired communication as well. But after digging into the wireless side, what I noticed is that the current or the conventional solution at that point, which was millimeter wave communication, was actually very lossy. And what I mean by that is that when you send information, there's a high chance that you lose a lot of your data, which means you have to retransmit the data. But our goal is to make things faster, not to slow them down. So basically it was like, how do I tackle that problem? But luckily, the team was already working with surface wave technology, which is a new communication platform, but it uses a waveguide. So you think about it as it's a specially designed waveguide that will allow the wireless data to be transmitted, right? So I sort of implemented that with the aim of addressing the lossiness in terms of the number of packets that we were losing when we are transmitting wireless data. And it was the first time that had been looked in that direction. And luckily, among the team, we've got antenna design experts, we've got other people working in wireless communication area or network on-chip area. I know Prof. Yakovlev is probably online with us. And Tuan also focuses on wireless communication in terms of the theory side. And then Terence and I continue the work that we were doing. Terence implemented a chip that was also very good in verifying the 3D ICs. So with my role, we managed to come up with new solution that we can send this data wirelessly over a longer period or longer distance. So with millimeter wave, we could go maximum 5 millimeters or 10 millimeters, then the signal becomes really poor. But we with these simulations that showed that we could transmit even much longer distance. And to me, that continued the work that I was doing for my PhD. And luckily, this led to 2 best paper awards as well. One mainly on the waveguide, which was new in the field in terms of the direction I took it. And then also the other one looking at how best we transmit the data within the chips. All this is showing is that with the surface wave, we get stronger distance coverage, while the existing one was lower, and then wired is good as some. So in terms of working in the on-chip area within the University of Northampton, Emmanuel is still continuing this work with me doing his PhD. Emmanuel is a member of staff now. And he's looking at the best way to optimize the power usage on the chip, meaning the best way that we can make our devices last longer on batteries. I think both Emmanuel and I know why he named one of his papers Abna, but in Ghanaian languages means a female born on Tuesday, I think. Yeah. And Emmanuel has won several awards as part of this work, and he's also won a best presentation with the work that he's doing. So I'm an embedded systems guy, which means I'm really interested in anything that you use or anything that uses a computer without you using it as a general purpose computer. So you think of a train ticket machine, you have a computer hiding in there, doing the logic decisions and other things, or when you're buying the ticket. When we were coming in, most of us scan our cards as well, so you have a device in there. So there's some form of sensing going on, and then there's some form of processing going on or making sense of the data that you actually sense from the sensors, right? And then there's a lot that we can do with the processed data. And this can span from AI to many, many fields, right? So anyway, any field that, think of any project or any implementation or any application that has to do with sensing data, making sense of the data, and making use of the sense data. So that's taking me to other fields as well, things like wearable computing. So stroke rehabilitation is one of my major interests as well. And a while back, I worked on a project with Ali, which uses wearable computing for stroke rehabilitation. So if you're thinking about stroke and other, let me use disabilities, that makes people less mobile. You don't want them going to the rehabilitation center all the time to do the rehabilitation process, especially if you are considering developing countries or a country like mine, Ghana, where you have to queue a really long time before you get access to the physician or a doctor to look after you, right? So the idea is get a patient to play a game in the comfort of their home. And whilst they are playing the game, because it's designed by us, I can get the data in the background, which is how many times they move their hand to the left, or they move their leg to the left or to the right, up or down. And the physician on his side will get access to all the statistics. Doesn't always have to see the patient unless there is a red flag, but the physician in the retrospectively can set the difficulty level of the game. And the difficulty level of the game will be, of course, adjusted to how well the patient is doing, or maybe how well they are not doing, right? So I've now teamed up with Roshni, and we are looking at how we can take this to well patients to do some testing, to do some adjusting to the design, to implement some AI to make the system more smarter as well. And we look at ways that we can keep helping people. This has contributed to 2 books, and also it's won a best presentation, the best paper in the poster session in a conference. So then that takes me to my MBA, and during that time I was obviously with the sensing part very interested in neuromarketing, right, which is basically the buy button of the brain, right? So if you think about it, if you're anything like me, you go to the shopping center with the aim of buying bananas, but you come back with a whole, I don't know, 3 bags or something like that. And the idea is, yes, using various advertisement appeals to get people to buy what you want them to buy, right? But addressing to the primal brain, not the thinking part, because one way or the other, we are all very primal, right? So my focus in there, I mostly use eye tracking, and this was just a test with a bunch of students. The experiments was done with separately with different individuals. And of course, there is scope for collaboration for people who are interested to work with me in this area. So I've mostly done the eye tracking part, or have been focusing on eye tracking part, but there are things with facial recognition or using facial coding, using AI. There are things like using EEGs, MRIs, and also people can measure the sweat in you. So basically they show you something and they ask you, what you feel about it. And most of the time, we don't know what we want. Whether we say yes or no, our body can tell a lot more. So with the eye trackers for the MBA side and the neuromarketing, I looked at various advertisement appeals. So basically, in marketing research, there are various appeals that they know attract people. And the question was, these appeals, do they actually do the job that the marketing researchers think it does, right? So with eye trackers, we can look at the human side. So this is coming from people, data from real people. And this is data generated from an AI to see how well the AI is doing in terms of its predictions. And this is data coming from the masses when they saw the paper, they saw the advertisement online to show whether they're interested in it. But the key thing I want to take from here is that it gave me a delve into working with eyes. And the interest continued beyond this. And I know Hilary is sitting right there, and I'll embarrass him by showing his picture. So Hilary is doing his PhD with me on a project. But before I do that, hopefully we all get a sound. I would like to play this short video because it's not work done by me, but I think it makes our case really well.
My greatest fear was realized when I was diagnosed with ALS at the age of 41.
You know, he's never sort of put himself in that spot where he feels sorry for himself or there, you know, he lessens his performance because of his disability.
3.5 years ago, our 21-year-old son and his girlfriend passed suddenly on a short kayak ride in the little river that our home backs onto. Speaking of driving with an eye tracking computer is the ultimate test of patience. It is quite slow even in the best circumstances. But when you have no other choice, it is a life-saving treatment. I hope that other people who have had loss and even tragedy can eventually find peace and joy in their lives.
I literally just found this video by chance today, but the interesting thing is, yes, I had to change things. The interesting thing is that he mentions that it's really, really slow, but when you have no choice, it is a life-saving thing. So for me, this project is actually closer to my heart, which means I see Hilary quite a lot, or call him quite a lot. But what we're trying to do is try to use AI to improve how the typing is done, to do some predictions, so they don't have to type in every single word. And of course, there are solutions out there, but we are trying to find the most efficient way that we can get things done. And that takes a bit of natural language processing and some machine learning as well. We are looking at other things with advanced motor neuron disease or other diseases that may get people, that make people less mobile. And so I'm working with Yingwei, who is also within the computing team, and again with Roshni this as well. And we have Hilary leading the work for his PhD. So I'm just leading the team. Then takes me to another eye tracking project with Harry. So I say to embarrass a little bit. I'll get a video to play on the side. We'll just loop only once, but I'll talk through it. So it's just basically combining photography with eye tracking. We've got a lot of projects that we are working on but this project is one that has also led to our first exhibition as well. I say mainly this is anything photography is area. I don't do photography. I do on my phone to myself and keep it like maybe a bit of Facebook. But then my role here is to use eye tracking. So basically when someone interacts with the image, people who are normally ignored in the room disappear. So creating that kind of effective cognitive recognition of what is happening here, and that leads to a lot of questions on that. And I'll say this one originally wasn't my idea, but I fell in love with the idea straight away. So I jumped into development of things, and we have other projects working on all around similar area, but things around like how, I'm not sure how much information I can disclose in terms of the projects we're working on, but things like, when the way it's perceived that beautiful people or people are perceived beautiful are more employable. So looking at all those kind of things to create similar awareness, but with interaction of AI and technology in there as well. And that takes me to the work of Chris. I know Chris has to go back to some country recently. So Chris is also doing his PhD with us. I've got Mo sitting there. I think Moya is probably with us online. And Moya is actually first supervising this project, and we are looking at looking at cataract, so using AI for early detection of cataract. We do have a contact in NHS who we are working closely with. So Chris started recently, and he's finalizing his first publication in this area, and we're looking at how we can push it beyond boundary. And this will be another longitudinal research that will be run within the institution. There's a lot of projects, and I do apologize, I can't talk about every project, but it's just a selection of some projects as well. Mostly the projects in networking. I know Noah is sitting at the back there. No, I'm sorry, I won't be talking too much about networking today, but I'm doing a lot of networking projects as well, and that's dating back to my PhD. You can tell that there's some networking in terms of what I do as far as my field is concerned. But I want to go on something that is closer to home. So going all the way back to my home country, which is in Ghana, and other developing countries, right? So this image is not that current, you can see, but it still proves a point to me, and it touches my heart. So the more green it is, or the more darker green it is, the more it means that these are the countries feeding the world. So these are the agriculture hotspots of the world, right? And you've got Ghana sitting on there, and Vietnam sitting somewhere here as well. So if we look at also in terms of the average income, you notice the more red it is, means the poorer the country is, right? These countries feeding the world are also the same countries that are struggling. And my country sits there. It's not the darkest red, but it's not too far away as well, right? And again, you can see Vietnam sitting somewhere there and also falling in the same area. But if we look, this is a bit tricky. This image is a bit tricky. If you look at the countries in terms of access to electricity, right? In terms of access to electricity, we've got Ghana being somewhat green here, which is really good to the rest of the world. It means that we're doing okay. But Ghana actually supplies electricity to neighboring countries as well. And as a result, what that means is that we also suffer from something called load shedding. So in a week, you can be without electricity in the whole area, really dark. Yeah. And this was so bad that sometimes it actually informs who is going to be the next political leader. In 2010 was extremely bad. In that time, I went back and saw at least know what was happening at that time. So it means that I grew up studying like this sometimes, right? You need a little bit of candle, and if you're not careful and you don't put the candle off, you get to burn a paper, which we eventually burn the house. Luckily, I'm here, and it's never happened to me, right? Okay, so first thing I wanted to do in this area is to look at how I can tackle the idea of load shedding, right? You've got the whole electric grid from generation to distribution. There's something I can do with smart technology. Maybe I wouldn't be able to solve the whole problem of huge generators. Obviously, it takes a lot of money. But in the house, we can do something like micro-load shedding. And as long as this fits into the utilities and everything, it means we can get a say, right? So what that means is that the electricity suppliers, if they switch off an area, they are losing money, because people are not going to use devices and the meters won't keep reading and they won't charge them money, right? And at the same time, if I've got food in my fridge, it's going to go bad. So it becomes the same issue that Emmanuel is currently solving on the chip, but at a macro level, which is, I can say I really like to keep food in my fridge. So as far as my priorities are concerned, keep my fridge on. You can switch off anything else. And the way we are tackling that is using smart metering. And it took an initial visit. Emmanuel did go with us, and Julius, who was the person that worked on the PhD, also went with us, and we did some visits to companies in Ghana to look at the best way that we can come up with load shedding, micro load shedding. And eventually, this project was sponsored by the government of Ghana, and Julius joined us. And he did a PhD, and he's completed the work now. And Eloho, who I couldn't find a picture of, but is sitting right there, is continuing the project. But I'll talk a bit more about it. And I've been working with Aldo and Ali on this area as well. This project and other projects also led to me getting the International Change Maker Award. So we've had some test beds in terms of retrofitting some existing smart meters to see how best we can save energy. The energy percentage savings was about 20%. This was in my home country as well. So all these projects I'm talking about are running, and there is one that is also very close to my heart, which is basically helping the countries like my country who are feeding the world to continue to feed the world, but other countries who can't because of maybe climate issues or whatever the issue is, maybe issues with soil, to also contribute to feeding the world. Or back home, I can grow crops all year round without actually worrying too much about it. So I got involved in this through actually a consultancy I did for Climo IoT, and one thing led to the other. I really love this, I want to continue, right? And it's going to lead to other things, and actually also won the Big 22, and Ray couldn't be here, but he's been very supportive of the project, and I'll touch a bit more about it. Prof. Tron, who is in Queen Mary's and is probably joining us online, he does a lot of IoT, but communication side and touching on smart farming. And that's the reason why I was talking about Vietnam earlier as well. So he leads us or gives us a link into Vietnam to work on this project. And I have Ghana, Kenya, that I'm also working on in this area. So the whole idea, this crops that I grew at home, and they all helped the little ones and their mom. So the whole idea is hydroponics, just growing with water, really clean way of growing. And because we are not using soil, insects lay their eggs into the soil, so mostly you don't need pesticides because we're getting rid of the soil. Right. It's not completely 100% organic yet because we use nutrient solution, but it's still a cleaner solution compared to growing crops. But with the sensors and embedded systems and control, I can create a controlled environment where basically you can tap some things on your mobile phone or tap some things in an app. Thanks, once you got your microphone turned on. And you can control things like smart home. You just say, Alexa, lights off and all those kind of things. You can control the environment. You can control the heating there, which means we can create the right temperature, the right climate that these crops, or mostly vegetables, need to these vegetables need to grow. So it means that all year round we get supply of food. It's leading into a spin-off, and I've had conversations about it. I had to slow down, so it's not started yet, but we've got test beds and also things set on the way. And projects from the smart metering and also energy management, all the way from things I've done on the chip level, contributing to this. But taking it to the next level of using AI in prediction, because a lot of data will be produced. There's a lot of sensing going on there. But on top of that, as part of the spin-off, the idea is that some of the profits will go to feeding the poor for free. Then use the word poor, or the less endowed in the public for free, when that works out as well. The idea is to use renewable energy, clean energy wherever we can, wherever I can. And that takes me to stuff I did in my education research, my interest in EDI, my interest in the award gap. Those who are not aware of the award gap, basically there is, in terms of the Black students are getting, or the minority students are getting, is far lower than that of the other students. So this has been a problem that the university has been looking into for years now, and other institutions in the UK have been looking into as well. My initial interest was with student engagement and other things, and those were stuff I did for my my MA. Then I met Patrice and Nathan, fell in love with the project straight away, and dig deeper, and we've taken it from just 1 year to become a longitudinal research, and we've done it for quite some years now, informed university policies around this area, and fed a lot into various groups in the JAM community and other groups as well, and done quite a lot of work in this area. In my thought, it's quite easy to sit behind a computer if you can get the code right, but normally it takes some time to get the code right. But once you get there, it's yes, and then it can run and you can walk around. I remember during my PhD, I used to walk around with this really old computer that I couldn't switch off because it wasn't powerful enough. And it would stay on for about a whole week, but the computer was doing all the work. Sorry if I talk too fast, I do that sometimes. So I get small captions, right? But in here, it takes hours because it's a lot of interviews, sitting around with people talking, but it's also the exciting part of the research that we are doing. So then, of course, where's Adi? I can see Adi. So yes, and Adi sitting at the back there joined us also, and we are looking at academic misconduct this year. I would say this year they're doing a lot of the work. That I would testify to that as well. So work in this area still ongoing as well. And of course, that led me to GEMA, and I became part of the cultural integration workshops. I think most of us are aware of the work that are being done in this area, but basically it's 8 workshops. And again, that is really, really exciting work. You can tell from the love at the background of the students that, yeah, it's been really exciting, it's been really enjoyable. And that it touches on most of the protected characteristics. I can go to more details. I can talk quite a lot about it in terms of what we do in the cultural integration workshops, but I would highlight that it's generated impact that I enjoy as well, considering my background or where I grew up with, and you can tell from the projects that I'm involved in, as far as I'm concerned, some of the things that are closer to my heart, beyond electrical, electronics, and computer engineering and computer science, right? And so working with GEMA, and of course, got Frank involved, and again, Nathan hiding there, and this has grown quite a lot, and it's become a train-the-trainer scheme. And last video I could have was with a change maker team, and of course this was recognized as the education change maker. Got the award. We got the education change maker award. So and again, we do have, of course, a bigger team behind us. Can't mention every single name, but it received a lot of support in that sense. So pretty much this is me, and I have to remember to put this slide up. Say thank you.
Thank you, Michael. Most people in the room know who I am, but for the benefit, first of all, for the benefit of people online, I'm John Sinclair. I'm the Dean of the Faculty of Arts, Science and Technology, and I have the tremendous privilege to be Michael's boss. which genuinely is a joy. So most people in the room know me as John, the Dean, colleague, but there is a clutch of people in the room who know me as the man who works with Michael, but who had the lovely dog. And the good news for Michael's family is we have another dog, so I'll see you in the park soon. And I look forward to it. Stunning, Michael, absolutely stunning. I'm sure we have questions. I will start on